Analysis and redesign of a hand drill by Team 13 with Marcus, Nathan, Michael, Zayed, and Albert. Starting with some background, you can see the drill there on the right in an isometric view. This is a manual hand-cranked drill where the drill chuck itself is loosened, a bit is placed into the chuck, and then the drill chuck is tightened, and then drilling can occur by twisting the crank. Depending on the bit, it can be used for wood, metal, or plastic. Similar products range from $20 to $25 on Amazon, but this is including the bit sets. As far as production volume, there's an estimated 70 to 100,000 based on Amazon yearly sales. Primary customers would be homeowners with limited craft experiences who are looking for safer, less scary, and less expensive alternatives. Secondary customers could be craftsmen with limited electricity access or the need for a lightweight backup drill. Here you can see the CAD assembly with the isometric view, but also top, bottom, and side views. Here you can see the exploded CAD, where we have bottom, top, side views, as well as the isometric view, showing all of the parts.
This is the fast diagram of the drill machine, which consists of primary function to create holes and secondary functions to generate rotation, control operation, assure dependability, assure safety, and please senses. The primary secondary function further expands to transfer power and generate torque.
Here we have our functional component mapping matrix, or FCMM, where all of the parts are charted with respect to their important functions. It can be seen that the functions of transferring power and defining motion have the most parts associated with them, so optimizing some of these parts that undergo these functions was one of our main focuses. Here we have our quad chart, which classifies each part based on their importance and cost. It can be seen that the parts with the highest function and cost include the spindle, drill machine body, bevel gear, and pinion. We are going to be analyzing and modifying some of these parts, which will be shown later.
From the fast diagram, we see that the main differentiator for these two groups is preventing fatigue, assuring comfort, and pleasing the senses, which leads to our platforms and modules, with our main platforms being the drill housing, the drill machine housing, and our spindle.
The kit for modules we have here, updated design and the initial design. The initial design basically had the crank that's connected to the gear housing and the bevel gear and with a screw, and that way you can turn this crank and basically it applies the torque and everything to the hand drill torque. Here we have just one piece, which is just a piece of metal, sheet metal, that's connected to a fastener and a bevel and a spacer connected to the bevel gear and to the hand drill, and then you can just turn it around. Basically makes the updated version easier to assemble and basically easier to mass produce. Common interface. Here we can see how they're all attached together. Right here, it's attached. We can see like how our thing is attached to the bevel gear, the updated model, and then here the crank, the old model, is attached. How it is.
So for the PFAD, we have the assembly sequence and the modified assembly sequence. For the assembly sequence, we basically have the bevel gear housing coming in the middle of the assembly line, it having two options. Basically, each option ends you up with a specific model. The modified assembly sequence, what we did was we basically moved the bevel gear housing up late in the assembly process, basically making the assembly time faster and the assembly process simpler.
We analyzed the assembly to find the highest impact parts on the manual assembly line. Two of the top three parts were the drill machine body and the spindle. As we can see on the quad chart, these parts are ideal for redesign. We also selected the connecting rod because we saw an opportunity for part consolidation with the spindle. As we can see, the spindle and the large handle connector share the same function to prevent fatigue and ensure safety, so we plan on combining the two components.
For design for manual assembly for the first part, the drill machine body, part 1, is shown here in the bottom left as an individual part, and the top right in an exploded view of the part of the assembly. After a design for manual assembly analysis, the hole for the spindle, part 2, goes through all of the part. In conjunction with changes to part 2, the spindle, we achieve a reduction in part count, and we add features for easy insertion. There should be no major effect on part function, and the die can be less complicated in manufacturing, which should drive down purchase costs for the die.
Now, moving on to the spindle and connector, shown by the two arrows, we can see that the four constraints are required to secure the spindle and connector into the drill machine body. This assembly draw the assembly time to be a total of 14.1 seconds. By consolidating the two parts, we eliminated the fasteners required to constrain the large handle connector. We also added chamfers to the part so it would allow for easy insertion during assembly. The assembly time was reduced from 14.1 seconds to 6.6 seconds. The redesign interferes with the drill machine body, so we modified the drill machine body to allow it to go all the way through. This redesign does not impact the part function but does increase the overall cost due to the part of the rod added to connect the spindle and the large handle connector.
Moving on to design for automated assembly. In our case here, we decided to go with the chuck assembly because it consists of mostly high functional importance parts that have high associated assembly costs with them. So now moving on, you can see here we've got the spindle, the drill machine body, and the housing connector in their original state, and their initial assembly cost was about $3.81. So now taking it through the DFA process here, we see that by introducing the part symmetry, DFA rule number 6 to part 1, we get a uniform part that has increased symmetry. And we see by taking DFA rule number 7 onto the connector here, we get a notch that helps facilitate the orientation of the component. And then taking DFA rule number 10, we apply that to the drill body here, and we get a chamfer that helps facilitate the location of the connector when we're inserting it. So taking a look at the overall product function here, we don't see any anticipated effects on the performance of the mechanisms. We do, however, see a decreased manufacturing cost because the spindle only needs to have threads cut into it now instead of being turned down. And with that said, our new assembly cost is $2.39.
So the first part was the drill housing. The process selection for that, we ran the process selection and we narrowed it down to machining and injection molding. Both of them were capable. We met as a team and then we decided to go with injection molding, hence being the selected process. Looking up on the right, you can see the dimensions of the part. We selected the tolerances to be 0.0128 inches, which is the standard injection molding dimensions for the overall dimensions of our part. Moving on to the drill housing, the DfM, after we ran the test on the DfM Pro, these were the results right here. And then calculating the costs per part, looking at it as injection molding and the material being ABS. Material cost came down to $0.041 per part, operating cost $2.37 per part, mold cost $0.316 per part, and then all that adding up to a total cost per part of $2.727. Looking at the drill housing DfM after these are the results we got after we ran the DfM Pro and the after design. It being injection molding and material and of ABS material. We came down to a material cost of $0.041 per part, operating cost of $2.37 per part, a mold cost of $0.143 per part, and all that adding up to a total cost per part of $2.554, basically saving us $0.173 per part. The changes we made were we made all the through holes, had fill it to the edges and at a direct angle. That way the spindle can just slide right through and hence easier and quicker assembly.
Now we are going to discuss the process selection for the spindle. Here we show the FCMM in relation to the spindle, where it can be seen that transferring power and defining motion are the two functions that the spindle is responsible for. Here we show some of the critical dimensions of the spindle in an engineering drawing highlighted in millimeters. We have chosen a tolerance of 0.005 inches, which is the standard for machining. It can be seen that the most important dimensions include the two different radii of the spindle, along with the length of the standard and spiraling part. Here we analyzed the differing manufacturing processes to determine which was most effective for the spindle, as a mild steel part. After highlighting the shape, mass, section thickness, and economic batch size, it was determined that machining was the only suitable process to be used for the spindle. In analyzing the spindle after DFA, it was seen that the machining cost was $1.52, the material cost was 23 cents, with a total cost of $1.75. DfM Pro highlighted a couple issues with the spindle design, in which we attempted to fix for the final design. In order to reduce costs and mitigate some of the issues, a few changes were implemented, including using standard stock, maintaining a uniform wall thickness, and reducing overall wall thickness. This created a cost reduction of 17 cents. The error of long slender turn parts was still present, but we believe that this can be fixed by clamping on both sides during the manufacturing process. After these changes were brought forth, the need for two radii in their critical dimensions was no longer present, but otherwise everything else stayed the same.
Product service systems. Firstly, the use of recycled materials such as aluminum, mild steel, wood, and plastics enable the product to be recycled at the end of its life. Additionally, design for durability can significantly impact the product's life itself and lengthen it to reduce waste. Additionally, providing spare parts can reduce waste by encouraging maintenance and therefore also lengthen the product's life. And additionally, having commercial partnerships and so cooperation between drill manufacturers and companies that create bits, so that way when a drill is purchased, you can purchase all the items needed at once, improving the customer experience and ensuring that drill bits are right for the drill.
To summarize, after a redesign, we were able to reduce the manufacturing time for our drill machine body, cut down automated assembly costs for the chuck assembly, and implement DfM guidelines to improve manufacturability and reduce manufacturing costs for the drill machine body and spindle. There are also a few critiques of our design. And if we were to start over again, we would put more emphasis on part consolidation and function component mapping matrices earlier, as it serves for a crucial guideline to the design.